Hello, guys. So today I'd like to, let's say, finally start to talk a little bit about quantum mechanics. Uh, okay, and quantum mechanics. So what I want, so it's a huge topic uh, from the historical point of view, from the theoretical point of view, and from the phenomenological point of view. So I will just start from an angle, and then later on I will add hopefully interesting facts or anecdotes or uh, even maybe simple examples. But let's um, let's see if I can give you a basic idea. So you remember when we so the first okay, first of all, remind ourselves that F equal m times a vectors is the equation of motion of, for example, an object. And then we studied a little bit, or at least we described a little bit, the motion of an object uh, subject to the force of gravity. Okay, so this was the g force, and this is our object with mass m. Okay, and F equal ma is actually a force, in this case mg. Let's do one dimension, and then mass the second derivative over time of the position. In this case, x is vertical axis. Okay. Okay, and then we want to find the trajectory, which is the position, and then there is some initial velocity v. Okay, and then we find the trajectory of this object by solving this equation. Usually, you integrate twice in time, and then you integrate again in time, and then you find your motion, which would be a parabola. Okay, so something like that. This is your vector x position in time, and this is the solution of your motion, and then you know that for each time that you pick, you can find the position in space of your object, and this is fine. And also, if you have the position, remember that it's very easy to find the derivative of the position of the t in the t, and this is the velocity at time t, which, by the way, is the tangent vector of this curve. Okay, so maybe we didn't go too much in detail about the fact that the velocity is the tangent vector of the trajectory, but if you remember about derivative, when you have a curve, you do the derivative, you take these two points, x1 and x1 plus h, and then you do the difference between these 2 points and you find a vector. That vector lies on the tangent space, so it's exactly touching the curve in one position, in one point, and basically that's the definition. So there is only one point of contact between your curve and your vector. Okay, and this is the velocity, which we know we can find. So basically, what I'm saying is that with F equal ma, there is no doubt that you can find x of t and v of t for each time, and then you can describe position and momentum at the same time. Okay, so the first thing that I want to clarify, that I want to say, that the first two things I want to say to make the jump from classical physics to a little bit of quantum mechanics. I'm not following the historical way, although I will give some details on where the first example of basically things that didn't work with classical mechanics happen. But the first thing I want to say is that there is an analog version of this equation, which is the equation of motion for your particle of mass m, and then you have what is called, this is Newton, and then there is what is called Schrödinger equation. Schrödinger equation is the derivative over time of an object, which we call psi, and we do a h bar h psi. Okay, so now let's write this psi in a different color, and then psi in a different color. Okay, so first of all, there is a clear jump between this equation and this equation. So some of you may notice that this is a first order derivative in time. So okay, so this is, we can already say that, and here there are second order derivative in time, and this is already some subtle difference, but it's there and I want to highlight. Then we notice that the object that we are dealing with is, in Newton laws, is x of t and also v of t, so which is the position of and the velocity of a mass object. So it's a trajectory with some vector that tells us the velocity at each point. Okay. In Schrödinger equation, what we have as a fundamental object is what I call psi. Psi is something that can be defined in every position and time. Okay. And first of all, is a complex number. Okay. So already you can see that the basic two objects here are essentially vectors in the real space. So is r real number to the cube, and then another real number to the cube. So there are 6 real numbers. If you think about the velocity and the position of an object. So there are 3 coordinates for the position, which you will locate in your reference frame, and then this is the position, and then there are other 3 coordinates for the velocity in each point. Okay. What happens here is that it's completely different in the scenario. At least for one particle, I'm talking quantum mechanics at the moment of one particle. So what happens is that you have to imagine that you have your space, your space and time, of course. We are not going relativistic here, so we are thinking about R3 gives us a position x at time t. Then sometimes passes, and then we we have in R3 we have a different vector x prime in T1 and so on. In x2 we have a vector T2 and a different position. But at this point here we associate a complex number z1, z2, sorry, I mislabeled them, okay, but z3. Let me go 1, 2, 3, where z is actually so z1 is, for example, a1 plus ib1, so it's technically two numbers with an imaginary complex. We saw complex numbers, okay, and these two numbers depends on x position and t as well. So essentially, for in each position we still have two numbers, but this is already geometrically different and like mathematically different and also physically different. Why physically different? Because basically this psi is not giving, psi x at least, is not giving you the trajectory, okay? So and it's not giving you the position either. What the trajectory, what's the psi means is what's called probability amplitude. Okay, this is a probability amplitude. Why probability? Because amplitude, because if you want to know what is, so the question is, what is the probability to find the particle in xt? So this is the question that we want to answer. What is the probability to find the particle in position x at time t? We know from what's called, I will say that again, it's a Max-Born rule. It's called Born rule, sorry, I don't remember if Max was what. Sorry, definitely Born, and maybe other contribution. Born's rule. Okay, you get that the modulus square of psi in x and t is this probability of finding in x and t. Okay, there might be some integration if it's continuous, but essentially the probability of finding in that position and that time is the square of this complex number. And we know what the square of a complex number is, okay? Because we remember that the modulus, so the square of the complex number is just the number by its complex conjugate. We can check our videos on complex number, but basically we have z times z. This is the product, the dot product, which is a square plus b square, where z and of course I need to define z, otherwise it doesn't make sense. Z is equal to a plus ib. Okay, and z star, the complex conjugate, is minus ib. Okay, if you do the product of the two, you will see that you get these two numbers. Okay, so as you can see, it's already conceptually different, because here we are saying that the best thing that we can give about a single particle is, for example, his mass, the mass, for example, yes, the energy, which basically is somewhat similar to the force in this equation. So the H, I will tell you in a sec what it is. It's the energy. That means what is acting, the interaction, exactly, that are acting on your particle. And basically pretty much H bar is okay. H bar is, I will so for a moment I will pause on H bar, but H bar is the Planck constant. Okay, it's basically fundamental constant in quantum mechanics, and is basically uh, a, the fundamental unit of measure that sets the scale of this these processes and these quantum mechanic effects, is somehow related to the minimum amount of energy per time that you can get for a quantum object, because, and also, I mean, it basically sets the, when it's 10 to the minus 34 joule per second, something like that. Okay, so it's a minuscule amount of time per second, per second. And okay, at the moment I don't want to dig into where it comes from, how you can derive it. I need to refresh that as well. But let me tell you that at the moment it's just something, just a constant physical, very important. But for what I want to say, it's just a, and then I place it in the wrong way, I think, because otherwise, oh yeah, sorry, and I place it in, as you can see, when you do dimension analysis, you get H bar. Here, H bar, it's energy, exactly. So otherwise it doesn't work out in terms of dimension, because this is energy times is energy, and this is energy, and this is a number, so it doesn't have. Okay, so sorry about that. Dimensional analysis. So Planck constant is basically the fundamental, if you want, unit of measure or scale at which these processes happen, and it's minuscule. You can understand that already this kind of effect will take place inside atoms or even below. Already at the molecular level, it's hard to find. There are, but it's more complicated to find quantum effect. Macroscopic quantum effects are very rare and very difficult to achieve, especially in laboratory, but there are. Lasers is an example, although it's kind of a niche example. Superconductivity or whatever happens in the hard disk drive, in your hard disk drive or any hard disk drive, there is a macroscopic effect on some atoms that react at the quantum level in order to store your information in your hard disk drive. There are plenty of examples in which quantum mechanics plays a role, but what I'm trying to say is that mainly the effects that are concerned are within very small space and microscopic distances. Okay, but what I want to tell you now is, and then I will other 5 minutes I will give a break and then do another session. What I want to say, so is the following. So the probability amplitude, which is it's a function of complex numbers that basically that will describe the physical properties of your object, subject to the interaction of your energy function, the Hamiltonian. Okay, now what is the Hamiltonian? In the Hamiltonian is the h function there. Let me erase this. So as you can see, we already said that um, this equation, the Schrödinger equation, uh, will tell you something about probabilities, not actually trajectories of x and p, x and v. Okay, so here we got x and v, and you can find both of them and each time. Here you will find only probability of x and t, and also probability of v and t. And it turns out, I will explain later on this, that you cannot get the same level of accuracy that you want in classical mechanics. So in classical mechanics, usually there is no issue or no problem, conceptual problem on having x position and velocity at the same time. Think about when you launch an object in air and then you take a flash with a camera, okay? You get the trajectory, you have a picture, and then you can extract the position and the velocity with your camera, and if you need a clock, of course, time that goes, and you measure the clock and the position, and I mean you can see that. I mean, it's clear that this is the way in which the speedometer works for car. They take pictures in two different locations, they measure the time, they know the distance, they know the position, the velocity every time, and they understand if you were too fast or too slow. Okay, this basically in quantum mechanics doesn't work anymore because I mean it's very subtle. I'm not going to do that in detail, but I'll just give you the highlight. It's basically impossible to define with with the maximum level of accuracy in both of the variable velocity and position at the same time. So this doesn't work. This is you cannot get. So you can specify one very precisely and the other will be blurred, or vice versa. And this is due to Heisenberg uncertainty principle. Uncertainty principle. Okay, I will talk about those things later. So yeah, so we touched upon Born's rule, which is the modulus of your object that you want to find. Modulus square gives you the probability of finding the object in that space, which is related to p. We say uncertainty principle. I will show you why you cannot get x and v at the same time as you would with the Newton equation. We touch about the fact that h is somehow the scale at which this process happens, so it's a very small amount of energy, meaning that we are dealing with teeny tiny object for a short amount of time, although there are plenty of examples at larger scale, but this is more subtle to explain. The idea is that those effect arose especially with small objects as a particle of light, for example, or electrons, things like that. So as you can see, very subatomic scale. And the other thing is that we touch upon is this h. H is the Hamiltonian. Basically, it's Hamilton was a mathematician and a physicist who described in a very geometrical way and in a very powerful way the motion of any object using these Hamiltonian functions, which are function of the energy interaction of the energy of the system. It's another way of writing Newton's laws. I'm not going to go into that. I'm just saying that this is a function of the energy, is equivalent of, to the energy, and the energy tells us what is acting on your object, what is the interaction that are acting on your object. But for what we need is a matrix. It's a matrix. I will. It can also be something different, but it can be a matrix, or what is called an operator when the dimension of the space is infinity. I'm not sure if I'm gonna touch on that in this video. Let's keep it easy. Let's suppose the psi is a vector, is a complex number. Actually, it's a pair of complex numbers. So C2, C square, so Z1 and Z2. This is psi. And the Hamiltonian is a matrix, a 2 by 2, in this case, a 2 by 2 matrix that acts upon your object. Okay. So once you define your interaction, whatever is happening to your object, you can guess, you can solve this equation. Okay. And just to conclude, I will give you a very simple example that I will use a lot for this case. So we said that it's a matrix, and we know how to exponentiate a matrix. You remember we did a video about exponential matrices. So if I tell you that the solution of this equation is e to the I t h, okay, this is the solution of ct, so position x, okay, this is because we basically integrate dx over dt plus a is equal to ax. As you can see, this is the same form as this one, and this is a nice solution, e to the ax, sorry, at, and if you integrate over time, and as you can see, this is already a nice easy solution for the simplest case, where you can get the exponential of a 2 by 2 matrices, and this and I think I will stop here, but so this is Schrödinger equation, and then this is in the case where the energy doesn't fluctuate in time, so it's a fixed kind of interaction, and then you can solve this with the trick that we already saw in other videos. Okay, so I know it's a lot, but remember, I will give a short summary of this, what we touched upon. I'm not saying that this is just a cold shower to flood you with lots of information and facts that are crucial to start to understand quantum mechanics. So we touch upon the Schrödinger equation. We said it's a complex number. We have the Bohr rules to get the probability of your position. We have a function of energy that it's kind of the force that is acting on your object. So it tells us the interaction, and then we know that this interaction is a matrix. It's not a vector as in the Newton's equation, is a matrix. A bit more complicated, but we can still integrate matrices because we know how to do it, and we can get a formal solution of this equation. Okay, so I know it's a bit maybe rushed as an introduction, but I hope that I picked up your interest. I will give some link to dig into more details for those who are interested, and see you next time. Bye.